Hey guys and girls, hopefully you're doing great. Please check out the description box for all the nice links. Drop a like, subscribe if you like the content, and check out the top right eye for even more nice links. This video is a very fun video for me to do because it allows me to speculate and talk about this amazing technology that's coming out. And a lot of you wanted me to take this PS5 Unreal Engine 5 tech demo and do a little analysis on it from what I know. Now, let me tell you from the start, I'm not a game engine developer per se. I have done it. I know how to make a 3D engine. I have made a 3D engine. I'm no way close to being the best at this stuff. But what I have learned is what is tough to do and why it's tough to do, and probably try to analyze these techniques that they are using here in this new engine and at the best of my ability. Maybe I have some input on it. It'll be cool to analyze and discuss this with you guys. And you let me know in the comments if I'm wrong, because I'll probably be wrong about a few things. So let's jump right into it. So what I'm going to do is I'm going to let you guys listen to this start here, and we're going to listen to them talk a little bit in the beginning because they say a lot of cool things.
I'm Brian Karras, Technical Director of Graphics here at Epic Games.
Hi, I'm Jerome Plateau, Art Director of the Special Project.
A few years ago, we got together as a team and brainstormed where we thought we could push forward the state-of-the-art in real-time graphics. There were two key areas that stood out. The first, dynamic global illumination. Beautiful bounce lighting, instantaneously.
I don't have to be constrained to do a game where the world has to be static, and I'm able to iterate a lot faster.
And we call this new system Lumen. We're about to show you what it is capable of. But first, there was another area that we thought we could push forward. Truly virtualized geometry. The artist wouldn't have to be concerned over poly counts, draw calls, or memory. We could directly use film quality assets and bring them straight into the engine.
And that's a big deal for artists. I just want to be able to import my ZBrush model, my photogrammetry scan, my CAD data without wasting any time optimizing, creating LODs, or even lowering the quality to make it hit frame rate.
In the end, that's what it's all about. Art that just works. And we call this new technology Nanite. Here is the future of Unreal Engine running live on a PlayStation 5.
Awesome. Let's take a look at it.
Awesome. Okay, so these guys are absolute geniuses. Let me just tell you that. So to start off, you get to see this amazing geometry. There's so much detail in here. And I'll pause the video right here. So what they said were two cool new systems they created, Lumen and Nanite. Lumen was the lighting engine and Nanite was the geometry engine right here. Now, let me tell you one thing. We got to base all this stuff off of one thing. Whatever hardware the PS5 is using is most probably stuff that you have in your computers today. So there's nothing new. The only new thing, there is actually one new thing, sorry, and that is the SSD. They haven't used the power of the SSDs before in engines directly. And that is because everyone doesn't have SSDs. They're not standard as of yet. Now they're starting to become standard, and gaming consoles of the next generation, PS5, Series X, they're gonna be standard SSDs. And you're probably not gonna store any game content on a regular hard drive anymore. Now, the big difference between a solid state drive and a regular hard drive is that there's no moving parts, and that allows there to be flash memory, which is very, very fast, incredibly fast. And the SSDs they're using in new technology, next gen consoles, are going to be probably read write of around 500 megabytes a second. And that is huge. That is absolutely huge. And that can be used in so many ways to stream data. A big problem has been to store a lot of your data in your RAM and your video memory, which gets capped easily, especially when you have 4K, 8K textures. And then when it's capped, you can't really put anything new in there. You gotta remove it and load it back in, and that takes a lot of time. Using all the hardware internal bus speeds, all these connections between the graphics card and CPU, there you have the fast speeds, but you can't really get it quickly from the hard drive where it's actually stored. So you gotta catch it in some way. You gotta cache it and put it somewhere, and that's where the RAM size really hinders you from using 8K textures and all that stuff. So let's keep watching here. I'll let them talk a little bit and then we'll analyze this.
Before we continue, let's stop a moment and take a look at some of the key features of this demo. Much of what you see was built with Quixel Megascan assets, but instead of using the game versions, we used the cinematic versions, which would typically only be used in film. There are around 1 million triangles each, and thanks to virtual texturing, they all use 8K textures as well. Nanite can render an insane number of triangles very quickly. There are over 1 billion triangles of source geometry in each frame that Nanite crunches down losslessly to around 20 million drawn triangles.
So what they're saying here, this is important. I want you guys to know. So a few hard things in game development is to remove unwanted polygons. You don't want even a triangle there that you don't want drawn, because that's unnecessary. Okay, something behind something, or maybe you're far away to see detail, that those pixels don't need that many triangles because you can't draw them anyway. And that's what it's doing. He's saying it's crunching down these art style assets, these directly imported assets, to these smaller counts of geometry. And that's very important to do that. And it's called culling. It's called culling because it removes unwanted stuff, basically. Okay, so if you look at the tunnel there, what's happening is the geometry you see behind the tunnel is only exactly the triangles you need to see. Anything that's hidden behind that little pillar there isn't drawn. It's not going to be drawn. And it's like an algorithm that just makes a tunnel, and it calculates from the camera position what should be drawn and not drawn. And that is very important. So they have some very advanced culling techniques, and it's very far away. So it's probably not a lot of triangles there to be drawn. And it's crunching those down and just in real time baking that in. And that tells me that these assets, he's saying that you're laser scanning an area. Okay, you can laser scan something, and that will give you so many triangles with such a huge size. You can't possibly put that on an 8 GB video RAM card. Impossible. You can't just put that in there and just stream it in there from your old hard drive. What is happening is probably they have a terabyte huge SSD, and they're live streaming from the SSD to the graphics card, caching what they need to cache and putting it into the RAM, whatever they need. Okay, that's probably what's happening. And that huge asset is stored in the SSD. Without that, this wouldn't be possible. And they're doing that, and then there's these real-time calculations happening on the graphics card. The graphics card is now free to calculate all that stuff instead of work with all this other extra geometry. So it's really helping out the graphics card to store a lot more data on there. And the graphics card is very fast. It's a very fast piece of hardware because there's thousands of small cores in there, unlike your CPU, which has 4 to 8, 4, 8, 16, whatever you want, threads and all that stuff. It doesn't matter. It's nowhere close to the amount of threads a graphics card has. So that is why we can render so much stuff at once.
What does that many triangles look like? These are the triangles, each a different color. Most are so small that they look like noise. Nanite achieves detail down to the pixel, which means triangles are often the size of pixels. This amount of geometric detail requires shadows to be pixel accurate as well, and Nanite can do that too. All of the lighting in this demo is completely dynamic, with the power of Lumen that even includes multi-bounce global illumination. No light maps, no baking here.
So he says something very important. No light maps, no baking. Usually when you create a static environment like this, you bake the lighting and you create light maps. And that means that there's no real-time light calculation going on. You're not using the graphics card power to calculate light. It's pre-baked. It's made in a way where the cave will probably not shift the light anyway. There's just one way the light will come in, and it will just pre-bake that into the texture and all that stuff. So you don't have to kind of calculate lighting. But what he's saying here is there's no pre-bake, there's nothing. Everything is happening real time on all these immense amount of triangles and textures, and the shadows are pixel accurate. That means that the light calculations are happening on that small pixel level. It's absolutely incredible. And what's going on most probably is they have some kind of ray tracing going on. Now, if you don't know what ray tracing is, you just heard it. You've heard RTX ray tracing and all that. Let me give you a TLDR on that. Ray tracing is basically rays casted from your camera towards a pixel in the geometry, towards a pixel, and then that's going to bounce towards your light source. What you want is you want to cast a ray for each pixel on your screen into the world, and that will bounce as it wants. You can tell it how many times you want the light to bounce, and it will recolor all the pixels depending on what it hits. Okay, if it hits something and bounces directly to the light, most probably that's going to be a white pixel. Boom, really clear. If it bounces a few times, doesn't really reach the light, it's going to be a darker pixel. So that's kind of how ray tracing works, and that costs a lot to do. So much calculation to do for the graphics card. So what they have done in RTX technology is put that on the hardware side. And what that does is it probably really quickly gives you a nice ray traced frame. And then you can use that data software in your software in your graphics card to kind of calculate stuff from that. And it takes away the heavy lifting of the graphics card. So it has a dedicated ray tracing chip, which does that really fast. And hardware is often, or always, much faster than software. And it can use different connections to the video RAM and stuff, where you don't have to do any kind of techniques. It will just directly fetch what it needs. And that's my assumption to this. They're using ray tracing, some type of ray tracing, maybe not as hardcore as RTX, but most probably you can't do this without any RTX card. I wouldn't guess you could do this without RTX cards and SSDs. Just keep watching.
All of that beautiful lighting is gone.
So see, it's not bouncing anywhere now.
We can move the light and the bounce changes instantly.
This is something you can't do with pre-baked maps. It really gives you a nice like illusion of it actually being dark there, like a real darkness and contrast, high dynamic range as well.
To our audio system as well. Convolution reverb allows us to measure reverberation characteristics of real spaces, like actual caves that we sample, and reproduce them in virtual spaces.
I love that they're talking about audio because it's not something I think about personally, maybe not what you think about either, but to make audio great, it has to be dynamic. It has to fit the environment you're in. If you're in an open cave, you don't want it to sound like a soundproof booth, right? You want it to be echoey and stuff. Now, what you could do is you could probably pre-bake that as well into the environment. But what he's saying here is probably that it's dynamic.
Sound field rendering allows us to record and play back spatialized audio. All of this adds up to a more immersive experience.
The only thing that kind of was lacking for me.
With our Niagara effects system.
Let's see this first though.
Particles in Niagara can now talk to one another and understand their environment like never before.
This is crazy, okay? Particles are a huge thing in games. Most probably you have one entity which you're rendering several times in a frame in different places. Okay, you don't want to load in 1,000 different rock geometries or rock shapes and then render them out. That's not what you want to do. You want to render one thing in several places really fast in one render call. If I remember correctly, it's called instantiated rendering, and it's one render call. And this is also a good background for you guys who are not game developers. When you tell some object to render to the frame, that costs a lot for the graphics card to do. It basically tells it, okay, place that here. And if you have thousands of particles and you're calling a render for each of those, that's really bad. That's really bad. So the technique people use in particle engines is they use one particle and they different color, give it different colors, shapes, rotation, sizes, all that stuff. And then they place them in all these places and they tell the card to render all that at once. One render call, and that means that there is only one render call for so many things, and it's really good for performance. And that's what's happening here. They have these smart algorithms, I guess, now where they can talk to each other, know the distance from each other. Flocking algorithms are very smart. They're probably using that. Particles really make the environment come alive. Like you can see all the stones falling are particles, the birds flying are particles. And this is something that was kind of lacking for me. Like if you look at the water, it looks kind of jittery and stuff, but it's not a big deal. It still looks good. You can really see the light pop, That's what you get. You have the high dynamic range here.
Here we are using it to accurately simulate the rigid bodies of the falling rocks and the cloth of her scarf.
This is something they improved a lot. The cloth is so much closer to the body now, and it doesn't clip through as much. And if you look at a scene coming up here where she climbs at her arm, where her arm touches it, it bends. You see it bends right there. It bent in a really nice way. It didn't just clip through or move to the side, it actually bent, so it's like fluid on her back.
We've added predictive foot placement and motion warping, which dynamically modifies IK and body position to look more natural. For the character to more realistically interact with the environment, we've added the ability to trigger seamless contextual animation events.
So I want you to look at that closely. Now, if you have a game like Fortnite, it has really good foot placement and predictive foot placement and animations, really fluid animations. What happens is when you have so much geometry and you're placing an object, you're placing a foot and you want to place it in a place first where it's supposed to go, kind of roughly, and then you fine tune it to really go down to the geometry. If you really look closely at this video, go back and look at it, where her foot is kind of stops at a point and it just slowly goes into the position it's supposed to go into. That is the predictive foot placement. I think they've really tuned that a lot more because it goes down a lot faster to where it's supposed to be. So that's really cool. And this is incredible, like the detail on every finger, how it moves.
The AI is amazing, not just for speeding up iteration, but also for its impact on gameplay. Any light source can move while still having beautiful bounce lighting. Dynamic illumination means specular as well, which...
This is great. Okay, this is something I'm going to tell you. Like when you have pre-baked lighting, you don't have specular lighting. Now what specular is, if you have a metal surface or any kind of surface that reflects something back, you're going to have a point on that surface where it reflects a lot of light back because it's very reflective. It's a metallic surface. And specular is very hard to do on a pre-baked lighting map because it's pre-baked. It's already set. You are not changing that light depending on where you are or where the camera is. It's there. So you usually don't have specular lighting on stuff that's static. Here you have dynamic lighting. So you can see all the geometry has specular lighting. Every object here, every little vase, everything has specular lighting. You can see it shining back to you. And that's where almost 100% of the light is coming into the camera. And it's diffusing. That's what makes a object look a lot more metallic. And that is called specular lighting.
You can see on all the metal surfaces. You can even see the Niagara-powered bugs reacting to the light. Lumen not only reacts to moving light sources, but also changes in geometry.
That is really cool. That is absolutely amazing. When you don't have pre-baked stuff, you have a light coming in. If the geometry changes, of course, the ray tracing will calculate differently because it's calculating real time. It will make a lot nicer, more realistic lighting situations here.
Remember we mentioned high poly assets? This statue was imported directly from ZBrush and is more than 33 million triangles. No baking of normal maps, no authored LODs.
So what they're saying here is baking of normal maps. All right, so this is a very important thing. When you have an asset, you have a lot of triangles on it. He said 33 billion or million, whatever he said. Huge amount of triangles. A normal is the vector that is perpendicular to that triangle. So it's kind of saying where the light kind of helps the light bounce, okay? And these normals are vectors you have to calculate by taking each triangle, taking 2 points of the triangle, two of these lines here of the triangle, and calculating a perpendicular vector to that. And that's costly even for one triangle. And if you're going to do that to 33 million triangles every frame, you're probably not going to be able to calculate those. So what you do is you pre-make these maps. You tell your rendering program to, okay, I'm done with my, or whatever object you're creating, make a normal map and save it in kind of a texture. It's different colors depending on which way the normals are pointing. It's like, it's a 3D object, right? And colors are of 3 values, red, green, and blue. So you can convert the positioning of that vector, the direction of it, into these 3 colors. And depending on the color in that pixel, that's where the normal is pointing, or the triangle. And that's how they pre-make these maps as a texture to the object, and you keep that stored. You can load it, you don't have to recalculate all the normals. Now, what they're saying is they're live calculating normals for this object with so many polygons. What I think is happening is they're cutting down, they're loading in the object with 33 million polygons, and they're cutting it down to just as much as they need. All right, they're streaming in data from the SSD to where the normals should point. Most probably they're using the graphics card and kind of storing that live, you know, cached somewhere on the SSD where they can just load this in. So they're making the normal map live, I'd say. You know what I mean? Instead of pre-making it in the program, they're kind of doing it live and storing it, still storing it where they can reuse it later, cached. That's what I think is happening. Not 100%, but that's my guess. Sorry for spitting all over the place. I'm really excited, bro. This is crazy.
And we can do more than a single statue. There are nearly 500 of that exact statue at the same detail level placed in this room, for a total of over 16 billion triangles from statues alone.
That's crazy. Again, culling, guys. Culling keyword.
There are hundreds of billions of triangles.
There are, but they're probably removing a lot of those triangles. Again, SSDs is the only new thing in the next-gen consoles. So having this leap in raw data, it's got to be SSD related.
So with Nanite, you have limitless geometry, and with Lumen, you have fully dynamic lighting and global illumination, all running on a PlayStation 5.
That's crazy. That looks great. I mean, it looks great. It does look great. It looks very detailed. Very, very detailed. Oh man. I don't see any aliasing, barely any. So there you go, guys. I mean, pretty much having this much data is raw data. That's what they're showing. It's lots of data.
It can stretch all the way to the horizon.
Yeah.
The portal, it's open. Don't fail me now.
Absolutely gorgeous. I mean, what can you say more about it? They have so much data. You you bet your patches are gonna be huge probably. If they give you a new model, if they use Unreal Engine 5, okay, let's make a new gun model for Modern Warfare 2 whatever. Yeah, that's gonna probably be a huge model for you to download. I mean, if they gotta give you these models when you buy the game, they gotta be on the disc, they gotta be on the digital version. And if the game is like 600-700 gigs big, you're probably only gonna have one game on your console at a time. If it's like how they're saying, they're probably still gonna optimize it and not use direct ZBrush models in their games, most probably because they're huge. And 8K textures, probably not gonna use them a lot, but we'll see. So that's my analysis, guys. I mean, like I said, they're probably not gonna use all this all the time in every game constantly. This is just what it can really do if you have unlimited storage space, unlimited SSD space. You can just use any you know, laser mapped area and all that. You put that directly into the game, sure, go ahead and do it, but I don't think games are going to work like this. What I can see happening is if you look at the PS5 version of Gran Turismo, where they're most probably laser mapping the tracks and everything, that's a lot nicer. You know, if you can do stuff like that and just import it directly, even the small bumps and details of a racetrack, that would be great. I mean, I can see developers doing that for racing games. Hopefully you get a better idea of how a game works. Like I said, I'm not an expert 100% in this. I work with game engines. I do create game engines that work with 3D, but this is so way above my level. Like I can only speculate. But that's my guess, guys. Hopefully you enjoyed it. Hopefully you learned something. Stick with me in the next video. Hopefully I'll see you there, and take care. I'll see you in the next one. Bye-bye.